morning, all. I'm sharing the PPT now. Is it visible?
Sir, visible, sir.
Yes, thank you, thank you. So today I want to discuss about efficient resource allocation strategies for star-assisted mesothelioma wireless network with physical air security. As a part of that, I want to introduce first of all what's the need of this norma and star is for next generation wireless networks, and what are the issues we are facing with respect to physical air security. I want to introduce first of all the system model. Then I will propose the methodology how to solve and all. Then what kind of resource allocation strategies we have proposed in our work that I want to explain with you. So this is the outline of my presentation. So I want to present some literature about this star risk and the norma with respect to physical air security. And these are some contribution works from our side, and I try to present with the given time, and we follow with the time. And first, I want to say evaluation directions for 6G. And any next generation wireless networks need to solve two issues every time. So one is energy efficiency, second one is spectral efficiency. So to solve spectrum efficiency, we are going for new kind of multiplexing techniques. As a part of that, NOMA came into picture. So to solve spectral efficiency problem of next generation wireless networks. And coming to before that NOMA, so we have OMA, orthogonal multiple access techniques, and we are having severe limitations with respect to that. We try to solve them by proposing NOMA, which doesn't require any orthogonality between the carriers, but the only limitation with respect to SSC, successive interference cancellation, every time. So we are considering this NOMA as a part of our 6 implementation to address spectral efficiency issue, and we are considering a new physical dimension, reconfigurable intelligent reflecting surface. IRS also they will call. So a reflecting surface who can act as an alternative path between source and destination. Whenever the channel between source and destination is not good in condition, we don't have direct line of sight communication between source and destination. We try to have alternative path. So that we are creating before this by cooperative communication by a relay. Now, even those relays can be replaced by restructures, reconfigurable intelligent reflecting surfaces. So I'm considering these two as a hybridization of these two, consider as a system model, and try to address the physical air security issue also as a system model. Why I'm considering physical air security also? Wireless medium is open to all. So in between source and destination, along with the authorization users, there may be a presence of unauthorized users too. So our information may leak to them. They overhear our information. So we try to every time calculate what is the efficient average channel information we are sending to receiver with respect to our own desired required users behalf of unauthorized users. So we try to calculate the amount of leak every time. If the leak is more than the amount of information we are sharing with receiver, then we try to have this physical air security issue. So only thing is how effectively we can send our information from source to destination. Behalf of these unauthorized users, we can explain in physical air security concept. So I'm proposing the basic principle of reconfigurable intelligent reflecting surfaces. I want to introduce that. So here assume that a base station which is operating in the range of millimeter wave or terahertz, it may be 5G or 6G. So I'm unable to communicate directly with the users because I don't have line of sight communication due to obstacle presence in between source and destination. The channel condition is not good. So I'm relying depending on an alternative path. So the alternative path now created by restructure. So this restructure is nothing but combination of a number of elements. So they can act as reflectors. So every time they modeled as they have a particular phase factor with respect to an amplification factor. So assuming that they are perfect reflectors, no absorption at all. So they try to redirect our own signal from base station to particular user's direction. So it can act as an alternative path creator. Previously, without this reconfigurable internal reflecting surfaces, there may be a application of cooperative communications. So cooperative communications may solve two kinds of problems. So one important thing is Cooperative relays can act as alternative path creators between source and destinations. So where there is no possibility of line of sight communication, that is possible by the presence of relay. At the same time, the relays can offer sharing of resources between the nodes in a network. So that means they can form a virtual memo. So instead of having multiple massive number of antennas at the transmitter and receiver, we can share our resources with the single users only and we can form virtual memo. So we can call this as one kind of diversity. It is one kind of spatial cooperative diversity. All the users in a network can act as relays except the source and destination. They can do two jobs at a time. One thing is they can transmit their own information. Along with that, they can help others to transmit their information to destination. So in that way, they are sharing the resources. They can form a virtual memo. Physically, every node assists with its own antenna. By comparing, by taking the share of other nodes, they can form a virtual memo. The virtual memo can offer all the advantages of physical memo. So cooperative communication has a particular advantage of having this cooperative diversity. But still, cooperative communication is suffers with how to select optimum number of relays and the impact of relay location and the type of mode of operation of each relay. So this, based on different factors, limiting factors are there. So that's why people are going for alternatives in 4G and 5G onwards. As a solution of that, we came to this resist structures, reconfigurable intelligent surfaces. Here there is a possibility to model, to program our elements of resist structure. Every time we can model them with respect to their phase by beamforming vector optimization, and we can scale their amplitudes in a particular direction. So based on that, we can try to improve the quality of signal receiver reliability from source to destination, base stations to number of users. In conclude, I can say so reconfigurable intelligent reflecting surfaces can act as alternative path creators where there is no direct line of sight communication between source and destination. And coming to resist structure types, basic resist structure type from the literature what I have. So a passive resist structure I have simply it act as a reflector without any amplification. So without any amplification, and see there is a factor of a phase shifter. Every time there is a controller to model the elements and all, and there is no limit on the number of elements all the time. So it's every time based on the application we need to identify what is the number of optimal number of elements we have to use. So if you consider only passive risk, it mainly concentrate on reflecting the signal in a particular direction without any amplification. Coming to active risk, so we have reflected signal with amplification. This amplification can be done by a particular parameter pi. We have shown in that is a amplifier plus phase shifter. But it is the always the limiting factor is 0 to 1. How to take optimum value of pi? How much amount of amplification we have to provide for incoming signal? That purely based on type of application again, how many number of signals we need to transmit and all. So active is always the difficulty with respect to how much amplification factor we need to avoid for this particular input signal. And the reflective only is it acquires a structure and reflected in a particular direction. And simple architecture, either transmitting purpose or receiving purpose, it is acting as only one side only. So maximum orientation of this one is 180 degrees. Maximum orientation of this one is 180 degrees. If I complete these two, transmitter and a receiver, actually you can say it is a one kind it is a transmitting, another case it is reflecting. So both full coverage of 360 degrees will happen. That can be called as star rays. So star rays will take the orientation for 360 degrees. It's a joint operation of transmission and reflection, and we have these two signal representations here: transmitted refracted signal and reflected signal from the user. So most of the cases, the star is the best possibility case we are taking. Along with active risk quality, we are adding to star risk. You can say it is active star risk. So star risk can occupy or it can send and receive the signals with overall coverage of 360 degrees. At the same time, it having the ability to amplify the signal and send it to the destination. And different receiver structures and their functionalities of a compare with respect to different parameters I have. Supported functionality, 360 coverage, reduction of path loss, thermal noise. equal RF change, energy consumption, equipment consumption. If I compare all possible cases of existing and I am comparing with the conventional relay in cooperative communication also, DFAF relays, decode and forward and amplify and forward, both conventional standard protocols we have under cooperative communication. We're highlighting the parameters like 360 coverage is possible with the star activities, and at the same time reduction of path loss is there under active storage because I can reduce the path loss by proper tuning of amplification factor by activities. At the same time, thermal noise, and we are not dealing with the circuit elements and all, and we are dealing with the protocols. So still, even though they are placing it as a factor of yes, so the consideration here is we are concentrating on a amplification factor by active storage. That's why I'm modeling that. And even another convention also medium we consider because compared to noise component here signal component we are making possibly as dominant by a proportionate amplification factor from active storage. And here, if a comparison of characteristics of amplitude and phase shift for various risk types, single functional risk, dual functional risk, active star risk. Every time, every node of star risk, a star risk or a risk structure consists of number of elements. Those n number of elements are mathematically represented by their amplitude coefficient with respect to their phase coefficient. So their amplitude coefficients are always in between 0 and 1. The stride factors are always in the range of 0 to 2 pi. So coming to star risk, if a single functional risk only oriented for 180 degrees, coming to dual function risk is star risk, oriented for 360 degrees. In one way it can act as transmitter, in another way it can act as reflector. So transmitter plus reflector, both the coefficients, the summation, the model as 1 and with respect to amplification coefficients. And with respect to phase shift values, always either transmitting or receiving, both should be in the range of 0 to 2 pi. It completes complete orientation of 360 degrees. And coming to active star rays. So the star rays parameters above these two are the same factors have. Only exceptional condition I have is active star rays. One particular coefficient I have in the range of 0 to pi. So it is only to amplify the transmitted signal with amplification factor. This amplification factor is the only difference between star rays and active star rays. We have to attain that we can get by optimization of this. And every node of this resist structure now should be modeled with respect to phase and amplification factors. That with respect to based on the number of users we have and the structure of domain of the node network. Coming to motivation, what are the what's the contributions I want to show in this presentation? The communication coverage can be extended to 360 degrees because I'm considering stars. So star is can act as transmitter for 0 to 180 degrees, and the remaining 180 degrees can be activated by receiver structure. Combined, I can collect as star is can cover for 360 degrees. Multiplicative fading effect can be reduced by introducing active risk with amplification factor. Main limitation of risk structure is this multiplicative fading. It is one kind of cascaded version of channels. That means how we mathematically model the structure channels is the effective version or the destination we can model as. So the channel is nothing but cascade version. The channel between base station to restructure and restructure to receiver number of users is always in the form of product of these two channel gains. So you can say it is a each channel now model under relay fading. So it is a double relay fading it falls under. So we can say it is a multiplicative fading effect. So multiplicative fading effect is the limitation of risk only because of this multiplication of fading effect. Signal variations are more. Signal variations are more. The signal is more faded. So it is our responsibility to boost the signal to make the signal component as more dominant component than noise component. In the process of that, I'm making it as active risk with amplification factor. This amplification of received signal, such a level we can overcome the limitation of this multiplicative fading effect. So the main reason for this multiplicative fading effect is nothing but cascaded version of the channel gain between base station to risk and the risk to destination. That can be somewhat overcome by this amplification factor. To consider real-time work concerns like non-ideal hardware components and some tolerances, value tolerances of circuit parameters we have. So those are also considered. and aims to fill crucial gaps, investigating the impact of practical phase shifts and hardware impairments and star risk configurations. So what we want to do now, so in the process of this one, we try to propose power allocations for normal users. At the same time, we try to propose practical phase shift because ideal phase shift case, we model all the elements are same in nature. Coming to practical phase shift, they are independent to each other. And how to model each element, amplification factor, and with respect to the phase factor. How to model that, we take it as a problem formulation. We try to solve that and see what are the objectives we form here. So we try to propose and analyze an active storage framework for wireless networks to achieve complete spatial coverage for 360 degrees and mitigating double path loss effect. This is a double path loss effect only because of the restructure cascaded gain. To propose power allocation schemes based on two. So we can classify power allocation schemes based on the nature of optimization problem we have. If the optimization problem is convex, we can directly go for linear programming kind convex optimization, and based on the non-linear type of optimization problem, some other cases we try to go for evolutionary algorithms or machine learning algorithms to try to solve them and their effectiveness and enhancing the ergodic rate. And physical layer security case, there are some presence of unauthorized users between source and destination. To overcome those unauthorized users leak information to them. So we have to make our channel gain more better than the weak channel gains. So to make that every time we need to calculate one parameter is called accuracy rate. So we try to define that and we try to analyze control jamming enabled storage framework for secure data transmission and normal presence of network with non-ideal hardware. So these things we are considering as objectives. I try to propose one system model and the methodology is the same for all kinds, just to try to introduce all these things. The first contribution from of the side, so the ergodic analysis and the power allocation schemes for a novel active storage aided wireless network. This is a system model I have considered with base station. The base station is now communicating with the far user and near user. Consider one as a storage case a transmitter, another as a reflector. And that is done by active storage. Amplification for transmitting signal also possible is there because it is storage covering for 360 degrees. And I model the channels. There are no direct links between base station and T user and R user. So that's why we are creating a line of sight path communication between them with the help of active storage. With the help of active storage. Now, the double fading is done by HSI and HIL. And we can model that channel links are both channel links IRS and IRS2 required users are both modeled with respect to that. So relay fading distributions with the path loss exponents and the corresponding phase factors and amplitude factors are models like this. The received transmitted reflected by n star element is represented by its amplification factor and with a phase factor of theta nt and the same procedure we are considering that square root of alpha n e power j. A particular amplitude coefficient of square root of alpha and with a phase factor of theta r. And they consider only the summation of these two factors, model them as one. So amplitude adjustments obey the law of conservation of energy. So that will be. And the combined transmission and reflection vectors of stars are represented by it's a diagonal with respect to that every element. They are modeled with respect to particular amplitude coefficient and phase factor. Likewise, there are presence of two possibilities are there. One way is to represent transmitter, another way is to represent the receiver. So combinedly 360 degrees of coverage. So for simplicity, up to now we modeled for node of a RIS and here amplitude factors are modeled as the summation as one and including the phase factors. And one more factor we have to introduce is amplification factor. Amplification factor from the star is that's why we call it as active star is. So due to its amplification, now it is getting done by PL, is the diagonal multiplication of this product factor. And where PI is greater than 1 denotes the amplification factor. Now I try to analyze the performance analysis. The methodology consists of how to solve every kind of this our network conduct. So first we try to have our system model. In the system model we consider the source and T user, R user and directly we are taking the help of active stories or connecting and try to do the performance analysis, mathematical modeling of the signal in the system. Then try to propose performance analysis in terms of performance metric. Here our performance metric may be some rate or outage probability or similar rate, sometimes throughput. So depending on the category, so select the performance metric and do the performance analysis. Try to evaluate. So for performance analysis, always we try to do mathematical modeling of the system and then try to derive expressions for signal to noise ratio and all performance metrics mostly a factor of signal to noise ratio effective SNR at the destination. We try to derive those things and we try to form the sum rate at the final case and we try to improve this sum rate. Maximization of sum rate we can consider as optimization problem. So considering system model is the first point of methodology. Second one is performance analysis. Derive expressions for sum rate and all performance metric. The third case, define our optimization problem. Your optimization problem we consider mostly so maximization of system performance, improve the system performance. That is nothing but maximizing the sum rate. So maximization of sum rate is nothing but maximizing the SNR. How to maximize an SNR? By having proper allocation of resources like power allocation or proper beamforming vector optimization. So these things we can further improve the signal SNR automatically that leads to improvement in rate of information or some rate. Some rate. So what we try to do, so as a first part of methodology, system model, performance analysis, problem formulation of optimization, and based on the nature of the problem, we try to classify the solution approach. So we try to select our solution approach. It may be convex optimization or evolutionary suboptimal soft computing. Sometimes with the help of neural networks, machine learning. Nowadays people are purely based on reinforcement algorithms. So see the nature, if we have the data set available, we have perfect CSI. So based on that, we try to go for optimization, compare our results with validate with the existing literature survey, and finally validate our proposed resource allocation algorithms efficiency with respect to conventional things. And till now, most of the works are limited to simulations and the mathematical analysis. And what left out is, if you want to convert these into a real-time prototype as a 5G or 6G test bed, you want to validate these in real-time platform. So try to have FPGA design, real-time validation for proposed power allocation algorithms or resource allocation algorithms. That's the only thing. So the gap always a bridge gap between academic institutions and industries where we are back in. So we try to have real-time implementation of these algorithms, protocols at the end, and FPGA, so real-time conversion. So the really will come to a prototype. So as a first part of this, we are taking our performance metric as this ergodic rate, right? That we are considering as a log of 1 plus effective SNR. So SNR calculations are completed. And see problem formulation I consider as maximize the SNR. Maximize the SNR. And the first constraint with respect to so star is, and at the same time it is a double fading channel effect, considering both the phase factor and the amplitude factor, so channel gain factor size, and with the source power and amplification factor P is equals to P, and we derive the formula in the form of a single variable and that ranges from 0 to 1. And here the nature of the problem we consider it as divide into particular parameter of a single variable optimization problem, and we try to solve that using Lagrangian multiplier method. So the final value solution we are getting it as in the form of approximated values with some approximations of A and B, C, D values, and that we consider. And if we want to do that, the subgradient algorithm. So the level of water filling level, so R Lagrangian multiplier value, we can found it by input values of all A, B, C, D values, and the parameters are considered, and every time we are updating. So only time is here the how much amount of scaling factor we have to take for updation of this one. They are considering the random values of initialization, 1.1 and -1. These are initialization taken as random values, and based on the nature of every time for a number of iterations, whether we are going towards the solution or moving away from the solution, according to that we have to select the scaling factor and update it. And for our case, it is working well for this particular condition. And at the same time, we solve the particular case, the optimization problem with the help of particle swarm optimization, also evolutionary algorithm. So we always know that. So this particle swarm optimization we deals with finding the number of solutions with better accuracy compared to convex optimization. But every time you run, it will give you a new result as a random case. So only thing is, with the limited parameters of PSO, we try to solve this and get better performance of PSO. And this PSO consists of consideration of range of variable. We need to find out optimum parameter cost function. So cost function is a parameter of particular here one particular variable alpha you can consider assume. So we first determine the boundaries of alpha and we try to update the number of population in the initial case. Group of birds, so you can say they are swarming with their intelligence. Every time they make a new movement with respect to their leader. So who attains highest cost function value, he becomes the local best for that particular instant. Likewise, n number of movements we will take for this group of particles we have considered. Every time they make a new movement, three factors will change. So they change their position, they change their velocity. At the same time, by substituting these new positions into a cost function, they will create new set of local best. New set of local best. So that's why I'm taking the primary positions of the particles are like this. Primary velocity is also initial assumptions. Every time we try to substitute these initial particles into cost function, so they try to produce a set of values. Who is strong among them in cost function value? That becomes local best at that time. Likewise, we can make n number of steps, n number of movements every time we make. So their velocities will update, their positions will update, and every time we update the positions, we check for the local best who is strong among them in cost function value. So that becomes local best. Likewise, for a number of steps, you will get a number of local best. One among them for all the iterations will become the global best. So this global best we can get after a number of iterations. The termination criteria may be based on the number of iterations or the number of particles they are meeting the particular threshold value. So PSO can work for more number of control parameters we have. At the same time, it performs better in the accuracy case and it converges fast. If we try to calculate computational complexity and the convergence of this particular algorithm, it performs well compared to most of the subcomputing evolutionary algorithms. So it converges fast. So coming to simulation results, what I considered for this one. So power allocation factor for optimized case for each value of n. I'm taking the n number of race elements value as 100 and increasing it to by a factor of 100 to 500. I try to see the difference between three. That means equal power allocation, blind power allocation cases, how the in each case, it is a constant value because it is a blind allocation. And these two are one is a convex optimization based power allocation, second one is evaluation algorithm based power allocation. This is PSO based, the second one is the Lagrangian multiplier method based. They are almost nearby same. If I compare these two with respect to the performance comparison almost they are nearby same. And coming to computational complexity. So PSO attains somewhat more convergence, fast convergence compared to Lagrangian multiplier method. So here the Lagrangian multiplier method also, we try to tune it and we can improve the convergence of this Lagrangian multiplier by proper value selecting of initial values at the same time the scaling factor for updation every time. Every time. That also we can do for every time possibilities. Here the considerations we are considered these are path loss coefficient, minimum we considered as a 2 and the transmission reflection coefficients of active star is in the range of 0 to 1. And noise power minimum minus 40 dBm I have considered and here even the both the cases and the signal to noise ratio range is 0 to 40 dB and if I observe number of reflecting elements are increasing I can get a better performance, but after some levels of n number of, so as the number of elements are increasing, there is increasing double fading effect also. So that's why probably it is not all the time the solution to improve the number of elements. At the same time, it is conditioned to validate how much impact of double fading effect is there. Even that also. And these are the parameters of PSO algorithms we have considered. Coming to some want to propose some simulation results here. You can observe ergodic versus SNR for a proposed transmission scheme. So improvement in SNR will improve the ergodic rate. If I compare with all possible conditions, I will get better performance for active storage coming to compared to remaining all. Even I have considered with the cooperative communication relay protocols, AF relay protocols, amplify and forward. So amplify and forward relaying protocol operation is easy, but the problem is along with the signal amplification, there is a presence of noise amplification too. And coming to passive star is it has actually don't have any amplification for the received signal. There is no minimization of double fading effect. So compare all these cases, I will get a better condition for active storage. Still, here I have not done any beamforming optimization. Here I deal with the only power allocation. So again, I compare with the active storage only, the proposed allocation with equal power allocation with the PSO based and Lagrangian multiplier method. Both evolutionary algorithm based and Lagrangian multiplier method based algorithms getting equal performance it seems to be, but there is a small bridge gap between them in terms of their computational complexity and convergence. So mostly, if I take the proper initial value selection for Lagrangian multiplier method, subgradient method, it convergence fast. But obviously, even improper tuning of PSO also will converge to optimum value, less than 20 iterations. So as the number of iterations, star elements are keep on increasing. So up to some level, they are increasing in terms of ergodic rate, but thereafter they are becoming seems to be constant. Why the reason is, even though there is improvement in number of star elements, the more number of star elements will leads to more double fading impact of resettlement cycles. So obviously, double fading effect will improve with the improvement of number of star elements. That is a limitation again. That means number of star elements should not be always more in number. It should be optimum number in such a way that multiplicative fading effect should be minimized by proper power allocation methods or proper resource allocation methods or by proper tuning of beamforming weightage factors. So I want to show that. So if it is the value is more than 600 for this particular cases, and even though there is a huge difference in number of elements, there's a limited improvement in ergodicity rate performance analysis. And concluding this particular system model, in this particular system model, I have considered Staris and with active Staris I have considered with the source and the T user and R user. I try to model the number of elements and their phase factors. I consider here it is ideal case modeling of all elements. Only how to assign power, active power allocation factor of source and active amplification factor of rich element. These two are tuned by Lagrangian multiplier method and particles from optimization method. And these two will perform better than conventional existing case data. And coming to second objective, I want to propose it as secrecy rate analysis and power allocation strategies for control jamming enabled storage from with non-ideal hardware. So this is a system model I considered. Here I want to introduce you what is the physical layer security issues we try to have. So here if you observe the system model, base station now broadcasting the information to required users UT and UR via status. Via status. So that means UT and UR both are authorized users, but there is a presence of unauthorized users too. One T user is the eavesdropper which is near to the transmitter, and here one more eavesdropper is there which is near to receiver. So that means our information may leak to these two eavesdroppers instead of required users UT and UR. How can I identify the impact of these eavesdroppers? So this eavesdropper impact I can analyze by a performance metric called secrecy rate. Secrecy rate. Secrecy rate, how we can define this one as this is the link capacity difference between the desired user and the leak user. That means there is an effective SNR for our required user UT. I can try to calculate the secrecy rate for this one as how much link capacity I have with respect to UT minus the link capacity with respect to eavesdropper. The difference between these two, the condition is always greater than zero. That means our main link capacity is greater than eavesdropper link capacity. That means information transfer is more than the leak. Information transfer is more than the leak. So it indicates a positive sign. There is no need to take any special consideration in terms of physical air security. So physical air security issues we try to solve with the help of jammers. With the help of jammers. What the jammer will do, the jammer will create intentional noise. Intentional noise. With this intentional noise, it will limit the performance of eavesdroppers. It will attack the eavesdroppers with the intentional noise created by the jammer. Intentional noise created by the jammer. So how I try to identify the impact of, first of all, we don't know where is the location of these eavesdroppers and all. And first of all, we need to analyze what is the impact of these eavesdroppers on the performance of our communication system. So every time I try to see the parameter accuracy rate. If accuracy rate is greater than zero, I try to go with the help of only our reserve nodes. And if accuracy rate, whenever it falls down the zero, that means when the leak is more than the actual transmission of information, so then there is a need of a jammer. So what the jammer will do, if you try to minimize the impact of eavesdroppers by continuously attacking them by intentional noise created by the jammer. So in this case, I have considered three possibilities. The three possibilities in the working condition. What are the three possibilities are? So without jamming case, but there is a presence of eavesdropper. There is a presence of eavesdroppers with respect to transmitter user at the same time with respect to receiver user. So two eavesdroppers I have closely placed, and there is a amount of lead to these eavesdroppers compared to our transmitter and receiver users. And I try to calculate the accuracy rate. I try to calculate the accuracy rate. Based on the value of accuracy rate, I can take the help of jammer. I can take the help of jammer. So without the jamming condition, there is no need of any jammer. Only there is a presence of eavesdropper and required users. So amount of loss is more in without jamming case because there is no jammer at all. Sometimes if the eavesdroppers are more close to users, so the amount of leak is more to them. Obviously, their link capacity is more than amount of information actually transmitting the required users is always more in amount. So that without jamming condition is the worst case where we don't have the jammer. At the same time, we don't know the location of eavesdropper, how close they are to with respect to required number of users. The second case I'm considering jamming case. So in the jamming case, jammer intentionally creating noise as information signal and it is attacking all the users. That means along with the eavesdroppers, even the required users also getting affected by this jammer. Because jammer creating intentional noise, it is broadcasting in all directions. So that means along with the eavesdroppers, original receivers also, they are suffering with the intentional noise created by jammer. So even in jamming condition case, we have an advantage of minimizing the impact of eavesdropper, but unfortunately, our required users also under the suffer of this intentional noise created by jamming. So that's why we are coming into third condition is called control jamming. Control jamming. That means where the required users know about the intentional noise created by jammer. At the same time, eavesdroppers don't know about that. So that means eavesdroppers don't have the knowledge about the jamming interference. Coming to required users, they know what amount of actual interference we are getting from jammer and all. So this is called control jamming. Because of control jamming, required users are saved from this intentional noise. Unfortunately, eavesdroppers will suffer with intentional noise created by the jammer. So these three conditions, we try to analyze the performance of our network. Without jamming condition case, there is no presence of jammer, only there is the presence of eavesdropper. And in jamming condition, so jammer is attacking eavesdroppers and required users at a time with intentional noise. And in control jamming, so jammer attacks the only eavesdroppers where the required users about they have the knowledge about this artificial noise created by the jammer and all. So control jamming attains always better performance compared to without jamming and the jamming conditions. So we try to model those things here. Here I consider only a single user, one single jammer, and one eavesdropper with respect to T, another eavesdropper with respect to R, and one single jammer I need to place. And model the channels as source to restructure as HSI, and we try to model with the path loss exponent and with amplitude factors, with phase factors and all. And we try to model them as relay fading channels distributions. And number of Solomons case, we try to have path loss exponent, their corresponding amplitude and phase factors are modeled like this. And we try to have received signal expressions, superimpose signal expressions at UI and eavesdropper respectively. So this is the double fading channel impact comes from resist structure. and this is the impact of noise. And one particular case we try to have from Jamal. So Jamal intentional noise also we try to include. And conditions, three conditions are considered: without jamming case, with the jamming case, with the control jamming case, with the control jamming case. Especially in the control jamming case, each required user have the knowledge about what the noise created by the jammer and all. But with the jamming case, all the users don't have the knowledge about artificial noise created by the jammer. And coming to without jamming, there is no jammer at all. Only impact of eavesdropper is there. Amount of leak is more to eavesdroppers compared to required users. In all the cases, I tried to calculate signal to noise ratio calculation for each case, and I tried to calculate accuracy rate. Accuracy rate is nothing but as we defined, it's the link capacity difference between the major authorized link and unauthorized link. Nothing but it's the link capacity difference between required users and the eavesdroppers. And what's the condition? This always should be greater than zero. This plus indicates take the minimum value as always zero and keep on take the value. If this rate is a negative value, so minimum value can start with zero and it can go up to whatever the rate. So what is our aim? It should be always greater than or equal to zero. The condition for the accuracy rate should be. That always it says that our direct link is more efficient than eavesdropper link. Amount of leak is less than or equal to the average channel information we are sending to receiver. So now under control jamming case, this is the SNR rate of information we model, accuracy rate we model. We try to improve this accuracy rate. We try to improve this accuracy rate. Improving this accuracy rate parameter shows that our main link, authorized link, is better than eavesdropper link. That means try to assign proper resource allocation methods, proper beamforming optimization methods. Aiming for that maximization of this accuracy rate is the problem formulation. Now I'm going for problem formulation. So maximize this is accuracy rate. Maximize this accuracy rate at the T user and R user can be stated as now it is a combination of three powers: source power and the jammer power. Source power and jammer power. And with respect to two factors I have. So it is a star race will cover in 360 degrees with respect to amplitude factor for transmitting case, reflecting factor for alpha R, alpha T. Their sum should be 1. And with respect to that, we are taking the three components of power: jammer power, and the transmitting power, and the receiving power. Every time the coefficients values are in between 0 and 1. And that defined optimization problem can be reformulated with the factor of log to make the conversion to alternative optimization problem. We consider the representation into another way. And this is the Lagrange multiplier method we have applied. So we try to find the value of alpha. The value of alpha is in between 0 to 1. Now it is a function of Lagrange multiplier value, and that's why we are going for a subgradient method every time to get the Lagrange multiplier value mu. So along with that, the same case what we have applied previous cases, so particle swarm optimization here I applied, but the cost function for this particle swarm optimization now is the accuracy rate of control jamming. Because without jamming, jamming and control jamming, these three cases, control jamming attains a better value. So control jamming attains a better value. That's why. So we are taking this one as cost function. So maximizing the rate is nothing but a minimization of this particular one. So I'm considering maximization of SNR problem as minus of minimization problem. And we try to improve selection of number of particles with the selected boundaries. And every time we try to move a new movement, I will try to update velocity position, and this new velocity positions will update every time will give you one local based set of number of iterations will give you set of local based. One storm among them will form the global based on the termination criteria. Based on the termination criteria. And here the simulation results, we have considered the parameters as Pathlas cost component minimum I considered as 2, and distortion noise parameters also, and signal is noise in the range of 0 to 40 dB. And here I consider is a linear topology of the network. That's why so model the distance in terms of meters and all PSO parameters. And coming to the optimization values of alpha factors for each method with a Lagrange multiplier method with the particle swarm optimization method I consider. And coming to for transmitting case, coefficient as 0.7 and it is 0.3. The optimum values and the Lagrange multiplier particles swarm optimizations are optimized So the values are given like this. And in value, the performance, they are nearby same. A slight difference is there in terms of their computational complexity and convergence. And here the accuracy rate analysis of power allocation schemes for number of elements in this structure are 100. And coming to here, the range is, we have taken three possibilities. The three possibilities are without jamming case, with the jamming case, with control jamming case, with respect to physical layer security. At the same time, with respect to kind of approach, optimization approach, we have considered two cases, Lagrange multiplier based particles from optimization. So we are comparing our proposed two algorithms resolution with equal power allocation without any optimization case. So three possibilities of comparisons with respect to kind of optimization. So Lagrange multiplier particles from optimization results are compared with existing without power allocation case. At the same time, without jamming, with jamming conditions are compared with control jamming. Among all possibilities, control jamming with the PSO attains better performance, and even it is nearby same with the Lagrange multiplier too, with a slight difference in initial value parameter tuning. At the same time, in convergence and computational complexity of these two. And if you compare again, the control jamming attains better performance compared to jamming, and coming to without jamming case, so it attains lowest accuracy rate. It almost even 30 dB also it is getting only 0.3, but coming to it attains a 0.8. And even we are comparing the star race for Lagrange multiplier and PSO and conventional thing, and even this one attains better performance in this particular case. And hardware conditions, just I'm taking the modeling of the parameters, modeling of hardware elements. So those two, one for transmitting case, another for reflecting case, a slight difference in the parameter values, the tolerance values. Those cases also control jamming attains better performance compared to, so remaining without jamming and with jamming conditions. And these are just mathematical modeling case where considered some parameter limitations as tuning factors, and these as hardware limiting factors. And here, we deployed control jamming enabled StarRace in NOMA-based wireless cooperative network to secure data transmission in the presence of eavesdroppers with effect of non-ideal hardware. The accuracy rates of NOMA with control jamming assisted, without jamming conditions are analyzed in the presence of eavesdroppers. Obviously, from the result, what we observed is control jamming have the knowledge about the jammer noise to required users. Obviously, it attains better performance compared to jamming and without jamming conditions. So, proposed a power allocation framework to maximize the accuracy rate under total power constraint and examine the comparative analysis of Lagrange multiplier and this without power allocation condition scheme, equal power conditions, and some non-ideal hardware components with a small parameter comparisons were considered in the examinations. So last class, resource allocation for practical phase shift. Till now we are considering ideal phase shift, practical phase shift also. So we are considering this one. And here also we have physical air security. And if I want to complete this one, so before that, instead of one eavesdropper, if I take a set of eavesdroppers, so multi-user environment, So the number of eavesdroppers number may be not one, it may be into group. So we can classify the impact of set of eavesdroppers into two types. How they are: collaborative case, non-collaborative case. Collaborative case, non-collaborative case. In the collaborative case, all the eavesdroppers together, that means they have coordination among themselves. They're together attacking the number of required users. That means that is called as collaborative eavesdropping case. Coming to non-collaborative eavesdropping case, all the eavesdroppers don't know about each other. They don't have knowledge about others. At the same time, they are independent. They are independent. They are individually attacking the required users. They are individually attacking the required users. That comes under non-collaborative condition. How to model these two mathematically? So in collaborative case, the impact of all these topics, we can take the sum. So impact of each, we can consider non-collaborative case, which is more dominant among in the group. So that impact we considered in non-collaborative case. So collaborative case, eavesdropper impact is more than non-collaborative case. That also a research challenge. Mathematically, you can model the number of eavesdroppers and their impact can consider at the required users. At the same time, we try to go for proposed power allocation schemes. At the same time, we try to model the impact of these eavesdroppers. That also can take it as a research challenge. And I want to propose some future directions because we're actually coming to the end of the session. So till now, we have proposed proposition of power allocation schemes at the same time. So beam optimization, practical phase shift optimizations for number of users in the presence of eavesdroppers and all. So in what way you can extend this work? You can increase the number of eavesdroppers. You can test the performance in collaborative case and non-collaborative case, where the more number of eavesdroppers are collectively attacking the required users, or without knowing each other, they are individually attacking the required number of users. In both cases, you can analyze. At the same time, till now we applied Lagrange multiplier method and some evaluation algorithms we applied. So you can take the help of machine learning algorithms and always try to take the real-time conditions as try to model. So practical phase shift methods you can go for and try to improve this non-ideal hardware component limits mathematical analysis also. At the same time, try to include it's a starless elements feeding of this one. You can make them as a self-sustain the nodes main. So by including new technologies like the Swift technology also, simultaneous wireless information come power transfer that also you can try to improve and analyze the performance in other performance metrics. You can try to include that one as a system model, try to make it as more customized. At the same time, do performance analysis in terms of new performance metric and go for so till now we have considered analog type or digital type. Go for customized beamforming techniques like practical phase shift conditions, and try to analyze where we don't have the perfect CSI. If I don't know the perfect CSI conditions, how to apply them also. And in norma conditions case, assume UT and UR. One among them as near user, and the second among them we consider as far user. Implement norma principle also here. And coming to physical layer security, how to select the required number of jammers, how to model the noise of jammers, how to make a problem formation and all, how to solve this with the help of machine learning also you can consider as a research challenge. And now finally I'm trying to concluding that here I consider a system model of star race. I included star race as alternative path where I don't have line of sight communication between source and destination. I'm taking the help of this active star race element. The star race will take the coverage of 360 degrees. At the same time, with this activeness of star race, will amplify the signal with a particular coefficient value. Try to model that also. With the proper modeling of channels, proper modeling of amplitude and phase factors of this structure, we always try to have better performance. And by having proper physical layer security algorithms, so which can minimize the impact of eavesdroppers and which can improve the performance of transmission to receivers in effective way with the help of jammers and all that also can take it as a research challenge. Thank you.
Thank you, sir.
Thank you, Maestro. How are you?
Fine, sir. How are you, sir?
Nice.
You have one more session, sir.
I think not on today, right?
Yeah, not today, sir.
Okay.
Thank you for the wonderful information, sir. We're looking for the other sessions also.
Thank you, Maestro.
Thank you, sir. The next session will start in few minutes. Please, all of you, stay back.
ఆర్సీ సర్క్యూట్స్ని నాకు 2 కేసులు వచ్చినాయమ్మా. ఎట్లా తీసుకురావాలి ఒకసారి చూడండి. వీడియో చూడండి.
సరే ఇప్పుడు అది ఫ్రీక్వెన్సీ బట్టి పేషెంట్ మారుతుంది. అక్కడ అది మారడం జరుగుతుంది.
ఫ్రీక్వెన్సీ బట్టి హై ఫ్రీక్వెన్సీ లో ఫ్రీక్వెన్సీ ఫస్ట్ ఏంటంటే పేషెంట్ కలిసి లో ఫ్రీక్వెన్సీ వచ్చినప్పుడు పేషెంట్ ఉంటుంది యాసిడ్ ఫిల్టర్ లాగా యాసిడ్ సర్క్యూట్ ఫిల్టర్ లాగా హై ఫ్రీక్వెన్సీ వచ్చినప్పటికి అవుట్ ఆఫ్ చేస్తున్నాం.
అది ఇప్పుడు మనకంటే పేషెంట్ అలా చేస్తుంది కదా సార్. ఆ ఫిల్టర్స్ కి ఎలా చేస్తుంది? అంటే బ్రేక్ వస్తుంది కదా అవుట్పుట్. అంటే ఇంకా దానికి కూడా తెలియాలి కదా ఫర్దర్ చేసే ప్రాసెస్ అవుట్పుట్ రేట్ వస్తుంది ఫాల్స్
డిజిటల్ సర్క్యూట్ ఉంటుంది
ఇప్పుడు ఇక్కడ వచ్చే బట్టి అక్కడ ఆపాలా.
ఇక్కడ గెయిన్ అనేది ఏంటంటే యాంప్లిఫై అయిన తర్వాత సిగ్నల్ కంటిన్యూస్ సిగ్నల్ కదా యూ వాంట్ హ్యావ్ దట్.
Next session will be starts within 5 minutes.
ఒకటి ముందు వెనక్కి వచ్చి
Please stay back.
1 0 1 2 0 బట్ ఇది కంటిన్యూస్ సిగ్నల్ కాబట్టి యూ వాంట్ హ్యావ్ దట్ ఇష్యూస్ డిజిటల్ సర్క్యూట్స్ మనం ఎక్స్పెక్ట్ చేస్తాం సెటప్ ఐస్క్రీమ్ మోడ్ అంత ఇష్యూస్ ఏం రావు. ఏ షిఫ్ట్ అనేది ఇంపార్టెంట్. ట్రాన్స్ఫర్ యాంప్లిఫైర్కి అంటే వీ టాక్ అబౌట్ ద గెయిన్ ఇన్పుట్ సిగ్నల్ కి ఎంత సిగ్నల్ అవుట్పుట్ వస్తుంది పెరుగుతుందా తగ్గుతుందా అనే పాయింట్ ఆఫ్ వ్యూ ఉంటుంది తప్పించి ఫేజ్ షిఫ్ట్ వచ్చినా ఫైనల్లీ వీ కెన్ మేక్ ఇట్ కాంపన్సేట్ చేయడం కొంచెం లీడ్ నెట్వర్క్ ల్యాండ్ నెట్వర్క్ ఏదో కనెక్ట్ చేస్తున్నారు. సో లీడ్ నెట్వర్క్ ల్యాండ్ నెట్వర్క్ పెట్టుకుంటే మళ్ళీ యాజ్ ఇట్ ఈస్ మన సిగ్నల్ కావాల్సి వస్తుంది ఫైనల్లీ వీ కెన్ చేయొచ్చు. సిగ్నల్ ఎక్కడ మనకి ఏమవుతుంది అంటే వీ లూజ్ అండ్ సిగ్నల్ అని ప్రాబ్లం. ఆర్సీ సర్క్యూట్ పెట్టాము ఇది అయిపోయింది కదా. ఇప్పుడు సేమ్ ఆర్సీ సర్క్యూట్ లో రెసిస్టర్ ఇక్కడ కెపాసిటర్ ఇక్కడ రెసిస్టర్ పెట్టుకున్నాం. నేను ఒక క్వశ్చన్ అడుగుతాను కదా ఇప్పుడు నాకు ఇంటర్వ్యూలో అడిగాను ఇది అయిపోయిన తర్వాత మళ్ళీ నేను ఇంటర్వ్యూస్ అటెండ్ అవ్వను 1 1 or 2 years 1.5 years తర్వాత మళ్ళీ మీరు ఏంటంటే ప్రొడక్ట్ బేస్డ్ కంపెనీ. సో ఈ ప్రొడక్ట్ బేస్డ్ కంపెనీ సర్వీస్ బేస్డ్ కంపెనీ ఈ సర్వీస్ బేస్డ్ కంపెనీ ప్రొడక్ట్ బేస్డ్ కంపెనీ క్లయింట్స్కి ఇంటర్వ్యూ ఇవ్వాలి ఇచ్చేటప్పుడు మళ్ళీ వాళ్ళు క్వశ్చన్ అడుగుతారు. మార్కెట్లో ఉంటుందంటే లైక్ అదర్ డొమైన్స్ లో అయితే ఇవ్వాలి. ఎలా డొమైన్ అయితే వాళ్ళు కొంచెం వర్క్ ఇచ్చేస్తారు నా ప్రాజెక్ట్ ఉంటే ప్రాజెక్ట్ లేకపోతే అప్పుడు మళ్ళీ మీరు అవుట్ సోర్సింగ్ ప్రాజెక్ట్ లేకపోతే అప్పుడు ఏంటంటే వాళ్ళు ఇంటర్వ్యూ చేసి పర్ఫార్మెన్స్ బట్టి వాళ్ళు మీకు ప్రాజెక్ట్ అసైన్ చేస్తారు లేకపోతే అసైన్ చేస్తారు. సో ఇది కంప్లీట్గా ఏంటంటే మీరు అప్డేట్ చేసుకోవడం ఉండాలి ప్రతి నాలెడ్జ్ ఉండాలన్నమాట. ఇక్కడ కెపాసిటీ కనెక్ట్ చేస్తాను సింపుల్ ఆర్సీ సర్క్యూట్ అన్నమాట. సో నేను ఇన్పుట్లో నేను వేస్తున్నాను ఇస్తే ఇక్కడ 1 వోల్ట్ ఇస్తాను 0 వోల్ట్ ఇస్తాను. సో ఏమవుతుంది నాకు కెపాసిటర్ అనేది ఫస్ట్ ఇనిషియల్గా చార్జ్ అవుతుంది అండ్ డిశ్చార్జ్ అవుతుంది. సో ఎక్కడ చార్జ్ అవుతుంది ఎక్కడ డిశ్చార్జ్ అవుతుంది ఒక టైం యూనిట్ ఇచ్చాను. టైం అంటే ఇక్కడ ఆర్ అనేది ప్లస్ సి అనేది ఇచ్చాను. ఆర్ అనేది 1 కిలో ఓం ఇచ్చాను. సి అనేది 0.1 మైక్రో ఇచ్చాను. సో నేను 10th ప్రాబ్లం సాల్వ్ చేస్తే నేను చెప్పేది మీకు అర్థం అవుతుంది. 10th ప్రాబ్లం ఉన్నప్పుడు సాల్వ్ చేశాను. మేనేజ్ అంటాను కదా సిమ్యులేషన్ పాయింట్ ఆఫ్ సిమ్యులేషన్ పాయింట్ ఆఫ్ నాకు ఇప్పుడు ఎలా వస్తుంది త్రీ ప్రో అనోటేషన్స్ నాకు చూపించాలి అవుట్పుట్లో.
ఇది కెపాసిటర్ పైన
ఇది దాని తర్వాత మోడిఫికేషన్ అనమాట. ఇది అయిపోయిన తర్వాత ఈ కేసు చెప్పాను 3 కేసులు.
ఇది చార్జింగ్ డిశ్చార్జింగ్.
For the first section, attendance link is given in the chat box. All of you fill the attendance sheet
ఇది వీళ్ళకి
for the first section.
మనకి ఇలా వస్తుంది. ఇది మనకి స్క్వేర్ లాగా ఇస్తున్నాం కదా పల్స్ అన్న స్క్వేర్
స్టెప్ లాంటిది ఇస్తే పీక్ డిటెక్టర్ లాగా
స్టెప్ ఇస్తే మనకి ఇది హైపర్సార్క్ సర్క్యూట్ కదా డిఫరెన్షియేట్ కదా. డిఫరెన్షియేట్ అంటే ఏమవుతుంది హైపర్సార్క్ సర్క్యూట్ డిఫరెన్షియేట్ ఏం చేస్తుంది ఇన్పుట్ స్టెప్ ఇచ్చాము అవుట్పుట్ అంటే స్పైక్స్ ఇస్తున్నాను అంటే మీకు ఎవ్రీ రైజింగ్ ఎడ్జ్ వచ్చినప్పుడల్లా స్పైక్ వస్తుంది, మళ్ళీ ఫాలింగ్ ఎడ్జ్ వచ్చినప్పుడు ఇంకో స్పైక్ వస్తుంది. ఈ రెండు మీకు అక్కడ అవుట్పుట్ జనరేట్ అవుతుంది. సో ఈ రెండు నేను ఇప్పుడు అవుట్పుట్ చూపించి ఇప్పుడు -3 volts వస్తుందని చూపించాలి. వేవ్ ఫామ్ లో చూపించాలి, ఈ అనోటేషన్ లో చూపించాలి, అండ్ మెజర్మెంట్ క్యాలిక్యులేట్ లో చూపించాలి. అంటే మీకు టూల్ అవేర్నెస్, టూల్ ఫ్లో తెలియడానికి. అది చూపించిన తర్వాత ఈ క్వశ్చన్ అడుగుతుంది. ఈ క్వశ్చన్ మీరు ఆన్సర్ చేయడానికి ట్రై చేయాలి. ఫ్రీగా ఉన్నప్పుడు దీని అవుట్పుట్ -3 అని చెప్పాను కదా, దీని అవుట్పుట్ -3 వస్తుంది లేదో చూడండి ఒకసారి. చూసి నాకు చెప్పండి, దాని తర్వాత క్వశ్చన్ అడుగుతాను. చేయండి.
ఇది లాస్ట్ ఎలివేషన్ ఉన్నప్పుడు తగ్గించడానికి వాసేజ్ తక్కువ టైం ఉండాలి.
ఆ తర్వాత క్వశ్చన్ ఏంటంటే ఇదంతా చేస్తున్నారు ఆన్ టైం 0 తీసుకున్నారు. ఆన్ టైం ఎంత అంటున్నారు మీకు 0.1 మిల్లీ ఇచ్చినప్పుడు ఎంతవరకు రైస్ అవుతుందో చూడండి. ఎంతవరకు రైస్ అవుతుందో చూడండి. -3 volts వచ్చింది. అప్పుడు ఎంత 63% రైస్ అవుతుంది. టైం కాన్స్టెంట్ 63%. సో 63% రైస్ అయింది కాస్త మళ్ళీ ఇంకో టైం కాన్స్టెంట్ ఇస్తే ఏమవుతుంది, 0 డిసైడ్ అవ్వాలి కదా, 0 డిసైడ్ అవ్వాలి, 37% డిసైడ్ అవ్వాలి. అలా 1 నేర్చుకునేది. ఇచ్చాను కదా ఇది, అందులో ఉంది కదా, అందులో 10th ప్రాబ్లం వేసేస్తే మీకు వస్తుంది. అది మీకు అంటారు. అందరు క్లాస్లో ఉన్నాము. ఒకసారి కలుపుతుంది. ఇది అంటారు అదే మాట్లాడుతుంటే నెంబర్ ఇస్తాను. అప్పుడు ఇచ్చింది కదా వచ్చి అన్ని పోలీసులు వాళ్ళు ఇన్వాల్వ్ కదా అవ్వాలి కదా. ఈ రెవెన్యూ మ్యాటర్స్ ఇది పోలీసులు పోలీస్ అయితే చేస్తారు. ఆల్పోస్ట్ ఫోన్ కంటెన్సీ తర్వాత స్టార్టింగ్ చేస్తే డ్రాప్ చేయాలి డ్రాప్ చేసుకొని అసలు ఫోన్ చేశాను. బతిమాలుకుంటే ఇంకా బాగుంది. కేసు ఇవ్వాల్సింది కేసు ఇవ్వదు. ఫస్ట్ ఏంటంటే జెన్యున్ గా మనం 5 లక్షలు జెన్యున్ ఇచ్చాల్సిందిగా కేసు ఇస్తుంది అనమాట. 5 లక్షలు మనం ఇచ్చిన 5 లక్షలకి మళ్ళీ ఇంకా 5 లక్షలు కాస్ట్ ఫీజు ఇవ్వడం, తర్వాత అకౌంట్ వేరే అకౌంట్ లేదు, అసలు అకౌంట్ చెక్ ఇవన్నీ చెక్ మళ్ళీ మార్కెట్ ఉన్నాయి, టైంకి చెక్ కార్డు ఇవన్నీ ఆడియో రివర్స్ ఏదో ఖర్చు. ఇంటికి వెళ్ళింది కదా ఇది ఎంత ఇంటికి ఏమవుతుంది.
గుడ్ ఆఫ్టర్నూన్ కల్పన. నాగేశ్వరరావు.
Madam, good afternoon, madam.
Good afternoon. Can I share my screen?
Yes, madam.
Okay.
నాకు తెలియకుండా చేసింది నాకు తెలియకుండా ఇచ్చింది నాకు చెప్పించింది వీడియో మొత్తంతో శ్రీనివాసరావు మీరు కలిపి అన్ని చేసుకుంటాం. మరి ఆడడం మొత్తం చేస్తున్నాను ఆడాలి.
Nageshwara, is it visible to you?
Yes, madam. Visible, madam.
Okay. Good afternoon, participants. Actually, this is the continuation of the last lecture, Index Modulation Techniques for Future Wireless Communications. Last lecture, we have seen some of the important concepts like what are the design goals in wireless communication or a communication system we have seen in the last class, and what are the design efforts in the like wireless communication engineers. There are many design goals, but I am concentrating in this lecture energy efficiency and spectral efficiency. High energy efficiency and high spectral efficiency is concentrating, and what are the definitions of energy efficiency and spectral efficiency we have seen, and uh, so what is the fundamental trait or relation between energy efficiency and spectral efficiency mathematical equation we have seen, and so this is derived from the using AWGN channel we have seen in the last lecture, and what is the relation between energy efficiency and spectral efficiency, how it is improved. Consider one multi-carrier system, multi-input, multi-output MIMO system. It's a 4G system. The same index modulation concept is introduced in 4G and beyond 4G, 5G and beyond 5G also. The same concept is introduced, and how the data rate is increased, and how to transmit more or additional information, and what is the difference between spatial diversity and spatial multiplexing we have seen. In the spatial diversity, it requires more bandwidth when compared to the spatial multiplexing, because in the spatial multiplexing, here we have two symbols. One symbol is transmitted by the one channel, and another symbol ST is transmitted by the second antenna. But whereas in the spatial diversity, each symbol is transmitted by antenna 1 and antenna 2, and again symbol 2 is transmitted by antenna 1 and antenna 2. It requires more bandwidth for here for transmitting the information or a symbols compared to the spatial multiplexing. In the spatial multiplexing, to reduce the channel bandwidth. So this is the spatial multiplexing encoder and decoder we have seen. The channel matrix is H, and S is the transmitted symbols, and R is the received signal, and N is AWGN channel noise. And how MIMO is not energy efficient, because the reason is if the number of transmitting and receiving antennas are increases, definitely the spectral efficiency is increases, but at the same time, each and because if all N transmitting and N receiving antennas are active, so each and every antenna, it is having or it consists of some electronic circuits like RF amplifiers, operational amplifiers and power amplifiers, which requires power to run and dissipate the energy. So to dissipate the energy efficiency of the system is decreases. So how it is like balancing both energy efficiency and spectral efficiency, because in the MIMO system, one of the drawback is MIMO is not a energy efficient system. The reason is when we are transmitting the symbols or the information, each and every antenna is active. So due to the active of each and every antenna, they will dissipate some energy. If all antennas are dissipate energy, the energy efficiency will be decreased. So that is the reason for MIMO is not a energy efficient system. If we want to increase the number of transmitting antennas, the spectral efficiency is increases. But at the same time, energy efficiency will be decreased. So how to balancing these both, and what is the trade-off in between energy efficiency and spectral efficiency? What is the solution is, one solution is we are not increasing the number of transmitting antennas. So that is not the feasible solution. So even if the number of transmitting antennas are increases, suppose for example MIMO 2 by 2 MIMO, 4 by 4 MIMO, 8 by 8 MIMO, or 16 by 16 MIMO, if the number of transmitting antennas are increases, spectral efficiency is increased, but energy efficiency will be decreased. So if the number of transmitting and receiving antennas are not decreased, even though the spectral efficiency increases and energy efficiency is not decreased, what is the solution means? Index modulation concept. In index modulation, one of the index modulation technique is spatial modulation. Spatial modulation I will show you in the further slides for types of index modulation techniques. So now I will explain in the last lecture, this is the last slide, spectral efficiency of spatial modulation technique. In the spatial modulation, maybe some textbooks they have written hello,
మేడం మీరు ప్రజెంట్ స్క్రీన్ కనిపించట్లేదు మేడం. మీరు
screen not visible.
విజిబుల్, నాట్ విజిబుల్ మేడం.
It's visible.
విజిబుల్.
It is visible.
ఓకే ఓకే.
Visible, madam.
It is not visible.
Okay.
So okay, sorry.
So the spectral efficiency of spatial modulation is SM is one of the index modulation technique. In spatial modulation, index modulation, or spatial index modulation technique. Some textbooks they have written capital R, and some textbooks they have written efficiency. So the spectral efficiency of spatial modulation is log base to m plus log base to nt, where m is modulation order or modulation number is m, and nt is number of transmitting antennas. Suppose for example, if m is equal to, in the BPSK modulation, actually in the index modulation, conventional modulation along with additional information bits are transmitted. So after explaining the concept, then how it is additional information bits are transmitted, I will show you. So m is the order. Suppose for example in the conventional modulation, BPSK is the conventional modulation technique. So in the BPSK there are two symbols, symbol 1 and symbol 2. Each symbol contains only one binary bit. Binary bit is 0 or binary bit is 1, because it is a BPSK modulation. In the BPSK modulation, log base to m is equal to modulation number is, our symbols are 2, log base to 2 plus log base to nt. Nt is equal to whether it is a 2 by 2 antenna or 4 by 4 antenna or 8 by 8 antenna. The number of transmitting antennas are, suppose if it is a 4 by 4 antenna. So the 4 by 4 antenna means nt equal to 4, and nr is also 4, because the same number of transmitting and receiving antennas in the MIMO system. So log base to 2 plus log base to again 4 by 4 antenna, it is equal to 4, 2 square. So what is the spectral efficiency? We can calculate. I will show you one example. Suppose for example here modulation is QPSK modulation. QPSK modulation means m is equal to 4, because there are 4 symbols. M equal to 4, order of modulation symbols, and log base to, the system of MIMO is same. Suppose if it is a 4 by 4 system, it depends upon the modulation, it depends upon the type of the or size of the MIMO, then calculate what is the spectral efficiency. So I will show you. So here, as clearly seen from the formula, the data rate bits per channel will increase using spatial modulation. By applying the conventional scheme on the above formula, we will only get 2 bits per channel use, but from the SM we will get 4 bits per channel use. So here, without using the spatial modulation, the normal only conventional modulation technique is used. Suppose m is equal to 2. So what is the spectral efficiency? Log base to 2 is equal to 1. Suppose log base to QPSK modulation 4, 2 square, it is equal to 2. So log base to 2 square is equal to 2. So without using spatial modulation, the efficiency is less when we are compared to the spatial modulation. With the spatial modulation, the spectral efficiency is equal to, without using spatial modulation, spectral efficiency is 2 because m equal to 4. With using spatial modulation, the spectral efficiency is equal to 4. I will show you one example, then it is clearly understand. So without using spatial modulation, here we are not having this term, only log base to m. So the spectral efficiency will be less. With log base to nt is added to log base to m, the spectral efficiency is also increases. So now from 4G to 5G, what are the increasing demands from 4G to 5G is the data rates will be increases and better quality of service, and fully mobile are connected like wireless networks, spectral efficiency, energy efficiency, latency will be less from 4G to 5G. And also there are like PAPR is reduces. So there are so many advantages when we go from 4G to 5G. So what are the solutions? So 5G wireless network will increase 10 times higher than the spectral efficiency, 10 times higher than the energy efficiency. This is only compared to 4G to 5G. From 5G to 6G also we are increasing spectral efficiency, energy efficiency, information rate or data rate or quality of service are connected many like mobiles and so there are so many advantages. The solutions are from 4G to 5G. There are 5G, some 5G waveforms are massive multi-input, multi-output is one of the 5G system, filter bank multi-carrier, and generalized GFDM, generalized frequency division multiplexing or multi-carrier system. And from 4G to 5G, like one of the system is NOMA is the system, and GFDM, UFMC, Universal Filter Bank Multi-Carrier is also one of the 5G, and millimetric wave communication is also 5G, and there are other 5G waveforms are also available in the existing literature. And the small modification of the 5G, suppose NOMA is not only 5G, so that is UAV is integrated with NOMA, that is also 6G communication. So it is slight modification from the 5G or extension of the 5G systems or 6G waveforms. So how the UAVs are integrated, whether the base station is, when the spatial multiplexing UAV is used for the base station. So like that only some small modification from the 5G, it is equal to a 6G system. So the one of the important like in the nowadays spatial multiplexing or index modulation techniques are used in 5G and beyond 5G wireless communication, because the spectral efficient, not only this is the solution, there are other solutions are also available, but this is one of the solution. By increasing the spectral efficiency and not decreasing the energy efficiency, we are both balancing spectral efficiency and energy efficiency of 5G and beyond 5G wireless communication system. One solution is the index modulation technique. In the index modulation, spatial modulation, even in index modulation concept is used in 4G and integrated systems also, like one 4G 5G is integrated, like 4G is integrated, OFDM and NOMA, are MIMO and NOMA, OFDM and MIMO. And so there is a integration of multi-carrier systems is one of the research area. And another research area is different index modulation techniques are used, and verify the performance of different systems with index modulation and without index modulation. And with index modulation, different index modulation techniques are compared. So what is the spectral efficiency, how it is increasing, and so these are the research areas in like wireless communications. And coming to concept of index modulation. Index modulation is a novel digital modulation scheme with high spectral and energy efficiency. So the indices of the building blocks of the considered communication systems are used to convey additional information. By using the index modulation, the additional information bits are transmitted. Suppose, for example, BPSK is the index modulation. BPSK is the conventional modulation. In BPSK, at a time, only one symbol is transmitted. So, whereas in the index modulation, additional information bits are transmitted along with the BPSK modulation. So how along with the BPSK additional information bits are transmitted is the concept. So first calculate what is the design steps or how it is index modulation is incorporated in wireless communication or multi-carrier systems. Means first calculate spectral efficiency is the first step. So I will show you the calculation of the spectral efficiency. So before that, in traditional communication system, information is transmitted by modulating the phase, amplitude or frequency of a sinusoidal carrier. In contrast, index modulation techniques enable transmitting of information by mapping the bits onto different entities of the system. So what are the entities means? One is modulation order and second one is index bits or indices bits. Then this additional diversity is exploited in order to transmit information. So how additional information bits are transmitted? So that I will explain. So moreover, index modulation techniques can be adopted as standalone or together with conventional modulation schemes. So there are, I will show you, explain that later, that slide. In the spatial modulation, the spatial modulation is first introduced by Mesla and Jagannathan in one of the research paper. And this scheme have regarded as possible candidates for spectral and energy efficient of next generation of wireless communication systems. And the multiple transmit antennas of MIMO system are used for a different purpose in an SM scheme. Suppose actually in spatial modulation, the information is carrying in two different units. One is indices of transmitting antennas and MRA constellation symbols. Not only MIMO, even in the massive MIMO or millimetric wave communication, so the concept of SM is same. So here our total information is transmitted, random total information is divided into two blocks. One is MRA constellation symbols and second one is indices of transmit antennas. So SM uses, what are the design steps for spatial modulation is, SM uses only one radio frequency chain is used. Radio frequency chain means it is just like a switch. So in between the transmitter and the receiver, we have connected one RF chain. Especially in the spatial modulation, we are using only one RF chain. Whereas in other spatial modulation techniques, maybe some spatial modulations, we are using two RF chains or maybe other more than two. In spatial modulation, SM index modulation, only one RF chain is used. That is one fundamental requirement. And second one is our information bits are divided into two blocks. One is antenna index selection or indices bits, and second one is modulation order. It reduces the hardware complexity and decoding complexity by using SM in whatever multi-carrier system, whether it is a MIMO system or massive MIMO or integrated systems. The hardware complexity will be reduced by using SM, and the decoding complexity is also reduces. And not only reducing hardware and decoding complexity, the intersymbol interference is also no intersymbol interference or intercarrier interference. So ISI is different and ICI is different. And now we can calculate spectral efficiency of SM system. Already I have given the formula. Eta SM or RSM is equal to log base to M plus log base to NT. So bits per channel use. So suppose I will consider 4x4 MIMO. NT is equal, you can calculate any size of the MIMO. I have considered 4x4 MIMO. The number of transmitting antennas are 4 and number of receiving antennas are 4. NT equal to 4 and NR is equal to 4. Using BPSK modulation, you can consider any modulation, either BPSK or QPSK or QAM modulation. So here I am using BPSK modulation. In BPSK, there are two symbols. So because the modulation order is equal to 2, symbol 1 and symbol 0. So what is the formula? The efficiency, spectral efficiency of SM is equal to log base to M plus log base to NT. So log base to NT is how many number of transmitting antennas here? I am considering 4x4 MIMO. So 4x4 MIMO means NT is equal to 4, log base to NT plus log base to M. M is here I am considering BPSK. In BPSK, the number of symbols are 2. So log base to 2, it is equal to 1 plus log base to 2 square, it is equal to 2. Log base to 4 equal to 2. 2 plus 1, it is 3 bits per channel use. The spectral efficiency of spatial modulation is 3 bits per channel use. So eta SM is equal to 3. So eta SM is equal to 3 here. So whereas in the previous formula is same. So here the spectral efficiency of SM is equal to 4 bits per channel use. So here M is equal to 4 because it is a QPSK modulation or 4 QAM modulation. In the 4 QAM or QPSK, the number of number of constellation points or number of message points are message symbols are 4. Log base to 4 plus the system is 4x4 MIMO system. Log base to NT is equal to 4. So it is equal to log base to 4 plus log base to 4. It is equal to 2 plus 2, 4 bits per channel use. If the modulation order is increases, spectral efficiency is increases. Or if the number of transmitting antennas are increases and spectral efficiency is also increases. So here the first step for index modulation or a spatial index modulation is spectral efficiency is equal to 3 because here I am considering BPSK. In the previous case, I am considering QPSK. The spectral efficiency is equal to 4. After calculation of the spectral efficiency, our random transmitted data is divided into how many number of bits. So there are the spectral efficiency is equal to 3 bits per channel use. It is divided into 3 bits for one section. Suppose for example, if spectral efficiency of SM is equal to maybe if it is 4, it is divided into 4 bits for here. Suppose 4 bits for one section. The first step for spatial modulation or spatial index modulation is first consider what type of the modulation is considered, whether it is a BPSK or QPSK or QAM, whatever number QAM. And next one is what type of the MIMO system, whether it is a 4x4 or 8x8 or 16x16, or if it is massive MIMO. Massive MIMO minimum is 64 transmitting antennas. NT and NR equal to 64. So now calculate the spectral efficiency first. After calculating the spectral efficiency of spatial modulation, then our transmitted data is divided into sections. So if the each section how many bits means, it depends upon the efficiency. Spatial modulation efficiency is 3 bits for one section. It is divided into the 3 bits for one section. After dividing the sections, each section, either you can assume MSB bit is the modulation bit and the remaining 2 bits for antenna index selection, or leftmost bit is, this is for assumption only, based on our assumption at the receiver side to decode the data. Here I am considering MSB bit or a rightmost bit is the modulation bit, and the remaining 2 bits for antenna index selection. And similarly, this is the modulation bit, and this is 10 or the antenna index selection. In BPSK modulation, at a time, we are transmitting only one symbol. So that's why the symbol 0 and symbol 1, it's a modulation bit. And the remaining 10 bits are antenna index selection. So now we are transmitting how many bits from transmitting station to the receiving? So there are 3 bits. With the help of the spatial index modulation, we are transmitting 3 binary bits at a time. Without using the spatial index modulation, we are transmitting in the conventional MIMO system using BPSK modulation, only 1 bit is transmitted because it is a BPSK. So the additional 2 bits are transmitted. So that's why the spectral efficiency is increases. So I will consider one example and explain. And even 110, this is the rightmost bit is modulation bit and remaining 2 bits for antenna index selection. And one more important question here. Suppose we are considering 4x4 MIMO antenna. In 4x4 MIMO antenna, actually how it is increasing the spectral efficiency and what is the solution? Because if the number of transmitting and receiving antennas are not reduced, but additional information is transmitted, we are not reducing because in the conventional MIMO, all 4, maybe 4x4, it is 4. All 4 antennas are active. All 4 antennas are transmitted by the same symbol. Whereas in spatial modulation MIMO system, only one antenna is active and only one RF chain is connected in between the transmitter and the receiver. The remaining 3 antennas are silent because the complexity will be reduces. Only one antenna is active. So how only one antenna is active, I will explain. Suppose here we have a 4x4 antenna. So from the transmitter side, 4 transmitting antennas. Whereas in the receiving side also we are having 4 receiving antennas. So in this example, BPSK modulation is used and 4x4 MIMO system, and efficiency is 3 bits per channel use, and our random transmitted data is divided into 3 bits for one section. 1 bit is for especially modulation order, and the remaining 2 bits is assigned for a antenna selection. So there are 4 transmitting antennas because our system is a 4x4 MIMO system. So there are 4 transmitting antennas. So one antenna is, because here 2 bits for antenna selection, 2 power 2 combinations. 2 power 2 means 0, 0, 0, 1, 1, 0 and 1, 1. You can assign 0, 0 is for the first antenna, 0, 1 is the second antenna, 1, 0. Or you can assign 1, 1 is assigned to the first antenna and 0, 0 is assigned to the, that is your wish, you can assign the 2 bits for each antenna. Maybe I can assign the second antenna is for 1 0 and third antenna is for 0 1. It is randomly assigned to each and every antenna. Suppose for example, the efficiency is equal to 4 bits per channel use. So 4 bits per channel use means 4 bits for one section. 4 bits means the modulation bits are, because it is a QPSK modulation, the modulation bits are 2 bits and antenna selection is 1 0 only. So 1 0 means again 0 0 0 1 1 0 1 1 is assigned to each and every antenna, but the modulation bit is equal to 2 bits for the modulation. Suppose for example, even in the BPSK modulation, and maybe if the number of transmitting antennas are increases, maybe antenna index selection is, suppose just you can assume 3 bits for antenna index selection 1 1 0. So 2 power 3 combinations, there are 8 antennas, each and every antenna is assigned to 0 0 0 0 0 1 2 power 3 combinations. It depends upon the number of antenna index or index selection bits and the modulation bits. So in our example, there are 2 binary bits for antenna selection and 1 bit for the modulation bit. So 0 0 0 1 and 1 0 and 1 1. So there is a RF chain only one. I will show you the block diagram of SM MIMO system. So there is a only in spatial modulation, only one RF chain is used. So if the number of RF chains are increases, the complexity is also increases. There are some drawbacks by increasing the number of RF chains. So only one RF, especially in SM, only one RF chain. If other index modulation techniques, more than one RF chain is also used, and output is equal to both modulation symbols and antenna index selection bits received at the receiver side. Actually, this is the general trans receiver block diagram of SM system. This is the incoming bits or a random incoming data. So the data is divided into log base to m plus log base to nt, whatever we have explained in the previous slide. So how many modulation bits and how many transmitting antenna bits, like here. So one modulation bit and antenna selection 2 bits, and symbol mapper and antenna index mapper or antenna index selection bits. So then it is given to a like whether it is what size of the MIMO system. It is NT by NR, number of transmitting antennas and number of receiving antennas at the receiver side to decode the transmitted bits at the output of the SM demapper. Here generally ML is a very simple detector. Instead of ML, you can introduce maybe machine learning algorithms or other detectors are also incorporated here, and compare the performance. So the simple and less complexity of the detector is ML detector. Instead of ML detector, you can introduce other detector, MMSC detector, or maybe so many detectors are available in the literature. You can introduce here with ML, without ML, or comparing of all the detectors. That is one of the performance metric parameter. And also not only BPSK, different modulation techniques are used. That is one of SNR versus DER you can compare. And with ML and without ML. Instead of ML detector, machine learning algorithms is also introduced here. So conventional detector and machine learning detectors. So you can compare. That is one of the research area. So instead of MIMO system, you can use like massive MIMO, and millimetric or OFDM MIMO or MIMO NOMA system you can introduce here. That is another research area. And instead of SM, you can introduce other modulation techniques and compare. That is another research area. So these are the research problems in, especially in this wireless communications. And you can change the channels also. instead of non-feeding channel. Generally it is a AWGN. So suppose you can introduce feeding channels, that is another research area, and you can introduce PA reduction techniques. So these are the research problems in the wireless communications. Actually, this is the general trans receiver block diagram of the SM. Same block diagram here. Channel, you can change the channel. So here you can use ML detector, or instead of ML, machine learning detectors. And one more problem is channel estimation also. Different estimation techniques are applied here, and that is one of the research area. So now the example of SM encoder is, suppose this is the random transmitted data, and the system is a MIMO system, like 4x4 MIMO system, and the modulation order equal to 4 means it's a QPSK or 4 QAM modulation. Calculate the spectral efficiency. The spectral efficiency is equal to 4 bits per channel use. Our incoming data is divided into 4 bits per one section. After dividing the section, again it is divided into two sections. One is modulation order, and second one is index selection. In the index selection, which antenna is active? Actually, in the index modulation concept is introduced in the MIMO system. There are NT transmitting antennas and NR receiving antennas. Only one antenna is active, especially in SM. One antenna and one RF chain is used. So in one antenna out of 4, because our system is 4x4 MIMO system. In 4x4 MIMO system, there are 4 transmitting antennas. Out of 4 transmitting antennas, which antenna is active? Either first antenna is active, or second antenna is active, or third antenna is active, or fourth antenna is active. So how to determine which antenna is active? And that particular antenna is transmitted by the modulation bit along with the index of the or indices bits. Suppose here m is equal to 4. M equal to 4 means there are 2 bits per message and 2 bits, because m is equal to 4 means QPSK modulation. In QPSK modulation, at a time one symbol transmitted, each symbol contains 2 bits. So this is first right most 2 bits for modulation order, and the remaining 2 bits for number of transmitting antennas, NT equal to 4. So already I have explained how it is divided. It depends upon the modulation and index bits. So there are 4 transmitting antennas. So the first antenna is assigned to 00, 01, 10 and 11 for the fourth antenna. So 11 is assigned to a fourth antenna. So that's why the fourth antenna is active. This antenna is transmitted by, actually this is the constellation diagram for the QPSK modulation. In QPSK modulation, the constellation points are 00, 01, 10 and 11. So here 10 means this is for 10. The modulation order is 10 symbol is transmitted along with, this is the information, 10 bits for modulation bits, and 11 fourth antenna is active. The fourth antenna is already assigned to 11. So 10 and 11 is transmitted by the fourth antenna. The remaining 3 antennas are silent. Suppose for example here 01, 01 for the modulation order. 01 means what is, this is the 01. Modulation order is 01. So the antenna is 00, 00 for index bits. 00 is already assigned to the first antenna. 00 index bits, and the message symbols are 01. 01 means this is the from the constellation diagram, the modulation symbols are 01, additionally 00. So there are, the first antenna is transmitted by 4 bits. Whereas in the third antenna, you can assign one is assigned to randomly, you can assign 00011011. That is your wish, you can assign based on the assigning of the binary bits, whether which antenna is active. So, do you understand, student participants? So, one more example is this is 0001. 0001 for the modulation bits and 00 is for the antenna index selection antenna. Which antenna is active? So 00 already assigned to transmitting antenna 1. You can assign 00 for the third antenna. So the third antenna is active. The third antenna is transmitted by 01 and 00. So there are 4 bits are transmitted without using the index modulation concept. So only using QPSK modulation, only 01 bit, only 2 bits are transmitted. So by using the index modulation, additional 2 bits are transmitted. So the total number of bits are 4 bits are transmitted at a time. So not only transmitting the information, but it is also, if it is not having 4 antennas are active, only one antenna is active, the remaining 3 antennas are silent. So it does not require power to active the antennas because they are silent. They are not transmitting any information. Only one antenna is active. Only that particular antenna is transmitted by the modulation bits along with the indices bits. So the more information is, instead of 01, additional 00 bits are transmitted. At a time, 4 bits transmitted by using this only one antenna. The remaining 3 antennas. So 3 antennas are silent means it does not require any transmission power to transmit the information of each and every antenna. Only one antenna, it requires power to transmit the 4 bits. So it will reduce the transmitted power. Not only reducing the transmitted power, more information bits are transmitted, the information rate will be increases. And also if the information rate increases means automatically spectral efficiency will be increased. If spectral efficiency will be increased in the conventional MIMO system, energy efficiency will be decreased because if each antenna is dissipate energy. But here they are silent, they are not dissipating any energy. So only one antenna is dissipate because only one is active. That antenna is dissipating energy. So because if it is not drastically decreasing the energy efficiency. So we are balancing, spectral efficiency is improved and energy efficiency is not decreased. So this is the advantage of index modulation concept, or especially in the spatial modulation. So coming to so ND equal to 4 by 4 and QPSK modulation in terms of the vector notation. So because if it is a QPSK, there are 2 modulation bits and the 2 index bits. We can be written as 00 to 111, and antenna index selection, which antenna is active, either first antenna or second antenna or third antenna or fourth antenna. At a time only one antenna is active. Suppose if it is a 4QAM and QPSK both are same, if first antenna is active, because if every symbol is having real and imaginary part of the signal, minus, there is a lookup table. This is the lookup table. So the first antenna is active means the symbol is -1 plus 1j, and the remaining 3 antennas are 00 means they are silent. Suppose if it is second antenna is active and the remaining first and third and fourth antenna is silent. So if it is available for not only this order, if different lookup tables are available, we can use this transmitting vector and transmitted from the transmitter. And detection of SM, the receiver of the SM scheme has 2 major tasks. One is detection of active transmit antennas and detection of data symbols, because our transmitted data is divided into 2 sections. One is modulation order or a data symbols, and another one is index symbols or active antenna transmit the indices bits. Separately we are detecting active transmit indices bits and data symbols separately. So one of the optimum detector is maximum likelihood detector is the optimum detector. So what is the detection of SM? The received signal is Y equal to HX plus N. General in the multi-carrier communication, the received signal is Y equal to HX plus N. Here X is the transmitted information or the transmitted symbols. In the transmitted symbol, it is having data symbols and index bits. I stands for the index bits and S stands for the separately we are decoding at the receiver side. And using AWGN channel, the channel mean equal to 0 and power spectral density is equal to variance is equal to 1. And ML detection rule is, this is the formula, argument of minimum of norm Y minus HX square is the formula to estimate index bits and data symbol bits separately. But here one of the research area is H. H means channel state information. Or suppose if the channel state information is CSI, channel state information is known both at the transmitter side and receiver side. Or CSI is known only at the transmitter side and it does not at the receiver side, or CSI is known at the receiver side. So because there are some conditions, suppose for example, if the channel state information is known and H is known and already we have received the Y, and calculate what is the estimated value of index bits and modulation symbols. Suppose the ML detection principle is Y bar is equal to HX bar plus N or Y equal to HX plus N. So in terms of the vector notation, this is the X bar. So what is the estimated uh, transmitted bit? X cap is the estimation of the transmitted symbol. Argument of minimum of Y bar minus HX bar square. So what is the error? Y bar minus HX bar norm square is the error. Suppose for example BPSK modulation is used. So there are two symbols, symbol 1 and symbol 0. So symbol 1 is mapped to a positive voltage level and symbol 0 is mapped to a negative voltage level. Or you can interchange. So S1, S2 equal to 1 and minus 1. So what are the combination of the transmitted symbols in the vector notation? Either 1 1 and 1 minus 1 and minus 1 1 and minus 1 minus 1. There are four possible combination of the symbols, transmitted symbols or a transmitted vector. Suppose 1 1 is transmitted. So if 1 1 is transmitted, calculate the error using this formula. Suppose if the CSI is known, we can calculate the error. That is error 1. Suppose for example minus 1 1 is transmitted. This is the transmitted message transmitted vector. Calculate the error. And 1 minus 1 transmitted. Calculate the error. There are four possible combinations of errors are calculated. Out of these four, which error is the minimum error? That is the best estimation. If the, suppose for example E2 is minimum error. So the minimum error is the corresponding transmitted symbol vector is minus 1 and 1 is transmitted. So the minimum error means what is the estimated value or X cap.
TCL scripts
So minimum error means maximum signal
TCL scripts
at the receiver side. So to calculate that is the estimated value of the transmitted symbol. So this is the simple ML detection principle. This principle is used at the receiver side of MIMO system. And there are some advantages of SM, simple receiver design and inter-antenna synchronization and inter-channel interference are completely eliminated, and high spectral efficiency and high energy efficiency. And there are some drawbacks like spectral efficiency of SM increases logarithmically. You know the formula log base to NT plus log base to M. So logarithmically with number of transmitting antennas, while the spectral efficiency of, especially in this V-blast, increase linearly with E30, and the channel coefficients of different transmit antennas must be sufficiently different SM, and there are some drawbacks. These drawbacks are eliminated. We go for the another index modulation techniques. These are the various types of index modulation techniques. Like extension of SM is concept is same, SM concept only. Only the difference is small modifications of SM, generalized spatial modulation, and multiple active spatial modulation. Multiple active means in spatial modulation, only one antenna is active, one RF chain is used. Whereas in the multiple active spatial modulation means, suppose if it is a group of antennas are active, suppose two antennas, one group, those two antennas are active and the remaining antennas are not inactive. And the generalized spatial modulation, only one antenna is active, but here we are using two RF chains. And quadrature spatial modulation, we are separately transmitting real and imaginary bits are separately transmitted. And generalized quadrature spatial modulation and modified generalized quadrature spatial modulation, these are the types of spatial modulations you can introduce. Like if you know the SM, and you can easily introducing with any multi-carrier system, instead of SM you can use GSM, MASM, and comparing. At least you can work on 2-3 index modulation techniques. It is sufficient for one thesis, or you can get very good SCI papers, because this is one of the advanced research topic, index modulation techniques in 5G and beyond 5G wireless communications. So I will stop it here. If you have any doubts. Nageshwara.
Madam. Okay, madam. Thank you, madam.
Okay.